Okay. Can you see the slides?
Yes, sir.
Okay. So today we will start about this operational amplifier. Okay, what is an operational amplifier, and what are its desired characteristics, and what is the block diagram, what is inside the operational amplifier. All those small details we will be covering. So operational amplifier, in short, it is named as Opamp. Okay, so this OP is OP, that is operational, and AMP is amplifier. So operational amplifier, the short form which we use commonly is Opamp. Okay, so this operational amplifier is a multi-stage direct coupled high gain amplifier with two differential inputs and single-ended output. Okay, so basically it is an amplifier only. Okay, it is an amplifier. Amplifier means one which amplifies the signal, amplifies the input signal. Okay, that is what is meant by amplifier. So operational amplifier is a basically an amplifier, but it has multi stages. Okay, it is a multi-stage amplifier. One or two or three stages of amplification itself will be there. Then it is direct coupled. Direct coupled means from one stage. Okay, there are, as I told, there are many stages. So from one stage to the next stage, it is directly coupled. There is no capacitor, nothing. Okay, directly output is taken from one stage and given to the input of the next stage. That is why it is called direct coupled. Okay, and the gain, it is the gain of the amplifier, total gain is very high. Okay, and there are two differential inputs and one output. So basically it is a multi-stage amplifier. Okay, it has two inputs and one output. It has a very high gain. Now, operational amplifier can be used to amplify AC as well as DC input signals. So it can work with both DC as well as AC input signals. Now, why it is called operational amplifier is it was originally designed to perform numerous mathematical operations. Like if you want to add two signals, if you want to subtract two signals, if you want to integrate a signal, okay, if you want to differentiate a signal, if you want to multiply two signals, if you want to divide, all those mathematical operations were actually performed using this operational amplifier. So that is why it was called operational amplifier, an amplifier which will perform mathematical operations. That is why this name was given. But later on, what happened is that many other applications of Opamp came. Okay. So now it is a very widely used IC actually. Now, with proper feedback components, present-day Opamp can be used for a variety of applications such as AC and DC amplification. You can design filters, which we will study in the coming classes. Oscillators, that also we will be studying. Okay. Comparators. All these are applications of Opamp other than the mathematical operations. Now, this we'll just look into the block diagram of an op-amp. Okay, since you are from computer science background, we will not be going into detail into each blocks and all. Just an overview only I will be giving. So first, what happens is that how many inputs are there for an op-amp? How many inputs are there? Do you remember? I told it is a multi-stage amplifier having how many inputs and how many output? Do you remember?
Two inputs, one output.
Two inputs, one output. So there will be two inputs. Okay, so first thing is that there are two inputs. I am representing these two as the inputs. So one input is known as the non-inverting input. Okay, the name of that input terminal is non-inverting input terminal. And the second one will be what? If one is non-inverting, other will be what?
Inverting.
inverting. So other will be inverting input terminal. So there are two input terminals. One is known as the non-inverting input terminal, and the other one is the inverting input terminal. Now this is given to an input stage. The block input stage block will be there, which will be having, which will be what is that? Having a device which is having a block which is having very high input impedance. Okay, so it is a input stage. Then from that also there will be two outputs. Okay, then it is given to an intermediate stage. From there, a single output comes. Okay, and then there is a level shifting stage, and then there is a final output stage, and from that you will get the output. So these are the blocks. Okay, very simplified block diagram only. Okay, very simplified block diagram of an operational amplifier. So input stage also is an amplifier only. Intermediate stage also is an amplifier. So these two are amplifiers actually. Okay, so input stage is having how many inputs and how many outputs? How many How many inputs are there for the input stage?
Two inputs, one
Two
output.
inputs are two output. Okay, so this input stage is a dual input balanced output amplifier, differential amplifier actually. Okay, that is manufactured using CMOS and transistors and all. So this in first stage is a dual input, which means two input, dual input balanced output, that is two output differential amplifier. Now intermediate stage, how many inputs are there?
Two inputs.
Two inputs and one output.
Okay.
So it is a dual input unbalanced output differential amplifier. Okay, so intermediate stage is a dual input unbalanced output differential amplifier. Now next stage is so the first two stages will be actually giving the amplification. Okay, very high amplification will be the result from the first two stages. Then you have the level shifting stage. Why it is used is because of the direct coupling between the stages. Okay, because one output is directly given to the input of the next stage actually. So due to this, what will happen is that the output might be shifted. Okay, if the actual output was supposed to be 1, it might be going to 3 volt and all. It will get shifted up or down. Okay, so what for that, the DC level will be shifted. So for that, to bring it down to the origin, okay, we are giving a level shifting stage. That is because of the direct coupling. Okay, since we are directly coupling, there is no capacitor for the coupling. That is why what will happen is that this capacitor has a property, it will block DC. Since we are not using capacitor, what will happen is that the output might be shifted up or down. So to overcome that, we will be using a level shifting stage. Then you have an output stage to take the output from. Okay, no detailed analysis or what is inside that and all for you, it is not required. If in electronics and communication engineering branch or other branches, electronics branches, it is required. Since you guys are from CSE, we are restricting it to this. Just the block diagram and a very brief explanation only is expected. So I have given here the details. You can see the input stage is a dual input balanced output differential amplifier. The two inputs are inverting and non-inverting input terminals. This stage provides most of the voltage gain of the op-amp and decides the input resistance. Okay. Now intermediate stage is usually another differential amplifier. It is driven by the output of the input stage. So input stage output from the input stage is given to the intermediate stage. Now this stage is a dual unbalanced output. Unbalanced output means only single output is there. That is why it is called unbalanced output. Okay. Then level shifting stage, due to the direct coupling between the first two stages, the input of level of shifting stage is an amplified signal with some non-zero DC level. So some DC will be added to it. So to overcome that, we are using this level shifting stage. Okay, so these are the blocks of an op-amp. Okay, so please go through it. It is just no detailed analysis and all we are not doing. Okay, what is inside the input stage we are not going into detail. Okay, we just know that it is a dual input balanced output differential amplifier. Intermediate stage is a dual input unbalanced output differential amplifier. Okay. So like that only is required. We are not going into detail about what is inside it. Okay. Now we'll come to the characteristics of an ideal op-amp. Okay. Now, first one is infinite open loop voltage gain. An ideal op-amp should have infinite open loop voltage gain. Okay, so that A is the variable that I am going to use for this voltage gain. So A should be equal to infinite. Okay. Practically, it is not so. For example, the 741 op-amp which we are using in the lab has a gain of 2 into 10 power 5. Okay, 2 into 10 power 5 is the voltage gain of the op-amp that we will be using in the lab. So ideal op-amp should have a voltage gain of infinite. Then second one is infinite input resistance. Okay, so infinite input, an ideal op-amp should have infinite input resistance. Why is it required? Is because to reduce the effect of loading. Okay, now op-amps and all normally where it is used is actually in instrumentation field. It finds a lot of applications wherein you want to amplify very weak signals. Say for example, signal from your what is it, ECG and all. Those signals will be in the range of microvolts and millivolts. Okay, so that are very small signals, and those sensors cannot actually give you any current because the voltage is very low. Correct. So if the input resistance is very high, what will be the current? If input resistance is infinite, if resistance is infinite, what will be the current? Can you tell me? Imagine what will be the current. Resistance is infinite. Then what will be the current? How is current related to resistance? I is equal to what? According to Ohm's law, what is I?
It's inversely proportional, sir.
So if resistance is infinite, what will be the current? You told inversely. So what will be the current? Resistance is infinite. So what will be the current? One, it will be divided by infinity. What is divided by infinity? Something divided by infinity. What is it?
1.
Something divided by infinite. Infinite means very large value. Correct. What is 1 divided by 10,000? It is 0.00001. Correct. So similarly, what will be 1 divided by infinite?
0, sir.
0. Understood. Which means that the op-amp will not take any current. Okay, it will not take any current. That is an important property of an op-amp. Okay, that is why the input resistance of an ideal op-amp should be infinite. Okay. Now, another is zero output resistance. Output resistance of an ideal op-amp should be 0. So all these properties you just remember. Okay. Then next is zero output offset. Zero output offset means if you are not giving any input, output should be 0. That is what is meant by zero output offset. If you are not giving any input, output should be 0. Correct. But in practical op-amp, it will not be. That is why this condition we are telling zero output offset. If you are not giving any input, output should be 0. Whereas for a practical op-amp, there will be some small output. Okay. In the range of millivolts and microvolts. Okay. Now, next is infinite bandwidth. Okay. Bandwidth should be infinite. Why we are telling bandwidth should be infinite means bandwidth means frequency range. Okay. So one op-amp you have. So that op-amp, if it is an ideal op-amp, it should amplify 0 hertz frequency as well as infinite hertz frequency. That is what is meant by bandwidth. Okay, whereas a practical op-amp will not amplify all the frequencies. Understood? Because it will have a frequency limitation. Now, suppose you have an op-amp which amplifies a signal of 0 hertz with a gain of 2. Then it should amplify 10 hertz also with a gain of 2, 100 hertz also with a gain of 2, 1000 hertz also with a gain of 2. Okay, going on 10,000 hertz signal also it should amplify with a gain of 2. 1 gigahertz also it should amplify with a gain of 2. Okay, so that is what is meant by infinite bandwidth. Infinite bandwidth means it should amplify all the frequencies with the same gain. Okay, that is what is meant by infinite bandwidth. Whereas a practical op-amp will not have that much bandwidth and all. It will be restricted to, say, it will be able to amplify signals only up to 100 kilohertz or 10 kilohertz. Okay. So that also we will see in our first experiment when we do in lab. You can see that it will not be amplifying any signals above a particular frequency. So please remember, infinite bandwidth means the op-amp should be able to amplify any signal with any frequency. Okay, a signal with any input frequency. That is what is meant by infinite bandwidth. Then the next ideal property of an op-amp is infinite CMRR. The last two properties we will be discussing in detail. Okay, when we come to the section properties of op-amp. Okay, for the time being, I am just naming it infinite CMRR and infinite slew rate. CMRR means common mode rejection ratio. Okay, these two quantities we will be discussing in detail when in the coming maybe next week or something. We will be discussing in detail what is that and all. Okay, so please remember these are the characteristics of an ideal op-amp. First one is infinite open loop gain. Second one is infinite input resistance. Third one is zero output resistance. Fourth one is zero offset output offset. Fifth one, infinite bandwidth. Sixth one, infinite CMRR. And seventh one, infinite slew rate. Of this, the last two we will be discussing in detail in the class. In coming classes, we will be discussing. Okay, so please note down this. These are the characteristics of an ideal op-amp. Okay. Now, this is the electrical symbol of an op-amp. It's like a resistor you will draw, transistor you will draw. Similarly, op-amp has a symbol like this. Okay, it is represented using a triangle like this. It will have two inputs. So these are the two inputs. Okay, and it has one output. And this is the supply voltage which we have to give to the op-amp for it to work. Okay, this one and this one, supply voltage which we have to give to the op-amp so that it will work. Okay. So can you tell me what will be this input? What will be this input called? It is shown here minus. Can you tell? Can you guess? What are the two inputs of op-amp? Do you remember in the previous slides? What are the names of the two inputs of the op-amp? Names? Do you? We told, right? There are two inputs and one output. What are the names of those two inputs? Anybody? There were two inputs, right? What are those called? It was called inverting and
Inverting, non-inverting.
inverting. Correct. Inverting and non. So can you guess me? Sorry, can you guess which is this terminal?
Inverting,
Inverting, because of this negative sign. Okay, correct. This is inverting terminal, and this one is the non-inverting terminal, input terminal. So first one is the inverting input terminal, and the plus sign. That one is called the non-inverting input terminal. And what will this be? This right side. It is the two inputs and what? This terminal will be the output terminal. Okay, this will be the output terminal, and these two are the supply voltage which we have to give. It is usually named using plus VCC and minus VE. Okay, sorry, minus VE. Okay. So you require in our lab also you will see that. Okay. So plus VCC and minus VE. So these are the supply voltages which have to be given, so that the amplifiers inside and all will get the proper biasing. Okay, because inside that you have transistors and MOSFETs and all, so they require power supply for it to bias. Correct. Biasing you might have studied in your first semester. So for that only we are giving this VCC and minus VE. You have to give one positive supply and a negative supply voltage. Okay, so this is the electrical signal of an op-amp. So everywhere we will be using this. So whenever you see this electrical signal, you should realize that it is an op-amp. Now this is the 741 IC which we will be using in our lab. Okay. So it is a 8-pin IC. It has 8 legs. That is why it is called 8-pin IC. Okay. Integrated circuit. So here this first pin is called offset null. Second pin is the inverting input terminal pin. Third pin is the non-inverting input terminal pin. Fourth one is where you give the minus VEE. Fifth one is again offset null. Sixth one is the output pin. Seventh one is VCC. And eighth pin is not used. Sorry. So please remember, this is the, okay, one more thing is required. Okay, here there will be a small dot actually. I forgot to put that. Let me put it now. Okay, one dot will be there. When you come to lab, I will show you. Okay, there will be a small dot like this. Okay, so that dot, wherever that dot is there, that is pin number 1. Okay, pin number 1, 2, 3, 4, 5, 6, 7, 8. So this is the pin diagram of 741 IC which we will be using in our lab. Okay. Of this, the offset null pin, okay, the offset null pin, that is 1 and 5, we are not using. Okay, we will not use it entirely for our course. So offset null pin 1 and 5, we will not be using. It has applications, but we will not be using. We will be using pin number 2, pin number 3, pin number 4, pin number 6, and pin number 7. So pin number 2 and pin number 3 are the input terminals. Pin number 6 is the output terminal. And pin number 7 is where you supply the positive voltage. And pin number 4 is where you supply the negative power supply. Is it clear? When you come to lab, I will physically show you the IC so that you will get an idea. And this Friday, anyway, I will show you in online lab. I will show you the IC as well as it connected. Okay. All those details I will. So Friday, Friday, if it is possible, please be present with your laptop so that I will introduce you to one software which is not multisim. Okay, another software wherein you can wire this for the time being. Okay. So I hope you understood the pin diagram. Any doubt in this pin diagram? Okay, it is a very small IC. Okay, black color. We will see in the in the lab. I will show you. Okay, physically you will be given each 18 students are there. So we will divide you guys into maybe 6 batches, 3 each, and you can, each will be given one IC. You can work using that. Okay. That time it will become more clear. Now this is the equivalent electrical circuit of an op-amp. Okay, so uh, these are the inverting input terminal and non-inverting input terminal. Okay, in between that you have the input resistance. Okay, for an ideal op-amp, what should be R in? Do you remember? Ideal op-amp, what should be R in? Input resistance of an op amp should be what? Ideal op amp. What is the input impedance of an ideal op amp? In the ideal properties we learned, right? Voltage gain should be infinite. Input resistance should be what? Forgot. Okay, input resistance should be infinite. Okay, and output resistance should be what?
0.
0. Okay. Okay, so this is the electrical circuit of an equivalent electrical circuit of an op amp. How it is modeled, and this one AVID. This is called a voltage dependent voltage source. Okay, no need to go. Anyway, we will not be using this equivalent circuit for this for your course. Just to know, just to tell you, I have shown. Okay. Okay, so output voltage, what is output voltage? Output voltage is the voltage at this point with respect to ground. So it will be AVID. Okay, so it is AVID because voltage at this point with respect to this point is AVID. So AVID. Because if you start from here, what is the first thing? There is no current because it is open, correct? It is open. So there is no current, so no voltage drop across R0. So only thing that is there is this voltage source. So output will be plus AVID. Okay. Now VID means voltage difference between these 2 points. What is that? Can you tell me? VID is the voltage difference between these 2 points. Here plus and here minus. So what will be VID in terms of V1 and V2? Can you tell me? VID, voltage here minus voltage here. What is that? What is the voltage here? V1. What is the voltage here? V2. So what is VID? Voltage here is V1, voltage here is V2. So what is the voltage difference? What will be VID? It will be the difference between V1 and V2. Okay. So V1 minus V2. So you can write output voltage as A into V1 minus V2. Where V1 A is the voltage gain, VID is the difference input voltage, V1 is the voltage at the non-inverting terminal, and V2 is the voltage at the inverting terminal. Okay. So please remember this is the equivalent circuit of an op amp. You have you have two inputs. Okay. Output voltage is equal to A into VID, where VID is the differential input voltage between these 2 points, that is V1 minus V2. Okay, so today's class is just an introduction to Opamp. Okay, we will then in coming classes we will be exploring more. Ideal transfer characteristics. So we know that output voltage of an op-amp is A into VID. Okay. So transfer characteristics means it is a relation between in output voltage and the input difference voltage. Okay. So suppose the voltage op-amp, or it cannot be infinite, correct? So let us take our 741 op-amp, which has a voltage gain of 2 into 10 power 5. Okay. So input, it will amplify the differential voltage with this much gain. Okay. Now let VID equal to 2 microvolt. Then what will be the output voltage? Can you tell me? Micro means how much? 1 micro is how much? 1 micro. Micro means how much?
10 power 6, I mean minus 6.
10 power minus 6. Okay. Milli means
3.
10 power minus 3. Correct. So what will be the output voltage? Can you quickly calculate using your calculator or something? What will be the output voltage? Output voltage is equal to A into VID. VID is given as 2 microvolt and A is 2 into 10 power 5. So how much will that be output voltage? Can you calculate? So it will be 2 into 10 power 5 into 2 into 10 power minus 6. How much is that?
4 into 10, say, 40.
4 into 10 will it come? 4
10
into
power
what?
minus
Uh,
6.
2
Oh,
into
yeah.
10. 2 into 10 power 5 into 2 into 10 power minus 6. Correct? So 4 into 10 power, what will it be? 4 into 10 power how much?
0.4, sir.
0.4. So it will be 4 into 10 power minus 1, which is 0.4 volt is the output. Correct. So now let us consider another case. So suppose VID is 2 volt. Okay. Suppose the input voltage difference is 2 volt. Then what will be the output? 2 volt, not micro, directly 2 volt. Then what is the expected output?
40,000.
So it will be 4 into 10 power 5, correct? This much voltage. This much voltage and all you will never get, correct? Okay, so it is not true. Okay, so it is not true. You will never get this much high voltage from a small IC like this. Okay, so what is the maximum voltage that it can get? Okay, that depends on the saturation of the voltage, saturation voltage of the op amp. Okay, so output voltage cannot exceed the positive and negative saturation voltage actually. Okay. These saturation voltages are specified by an output voltage swing rating of an op-amp for a given value of supply voltage. I will explain in detail in the coming slide. Okay. So please remember that it will not go above a particular voltage. Understood? You will not get 4 into 10 power 5 voltage and all. 4 into 10 power 5 voltage means it is a very high voltage. Okay. You will never get that high voltage and all as the output. So it is limited by the supply voltage that we are going to give. Okay. So it depends on what is the VCC and VEE that you are going to give. What will happen is that suppose you have VID like this, okay, in the x-axis, and in the y-axis you have the output. Okay. So for a small range, if the input voltage is very small, you will get the amplification as proper. After it reaches, if the when the output voltage reaches a particular voltage, okay, it will not go above that voltage. It cannot. Okay. So that is what is meant by saturation. Okay. So this point is the positive saturation voltage, which will be less than VCC, that is the supply voltage we are giving to the op-amp. And here, this is called the negative saturation voltage, which will be again less than the minus VE. Clear. So between these 2 points, it will be working as an amplifier. And after that, it is going to what is known as the saturation. Whatever high voltage you give, output will be maintained at that particular saturation voltage. Is it clear? You got an idea? When you are giving a very small voltage, okay, it will work. But after that, it will saturate.
Yes, sir.
Okay. Now let us quickly find out what is the saturation voltage. Okay, and we will wind up. Okay. So saturation voltage, okay, will be almost equal to 94% of the supply voltage. Okay. So it cannot go above that. If the output is 100 volt and the VCC you are giving is 15 volt, it output will be less than 15 volt. Okay. It cannot go above that. Okay. So usually it will be 94% of VCC. So suppose VCC is 15 volt, then positive saturation will occur at 94% of 15, which is 14.1 volt. which means that output voltage cannot go above 14.1 volt. Is it clear? Suppose for an op-amp, you are giving supply voltage 15. Okay, it means that output cannot go above 14.1. If the output is going above 14.1, what the op-amp will do is it will limit to 14.1. Is it clear?
Yes, sir.
Okay. Similarly, suppose you have 12 volt as VCC, then what? How much will be the? Can you quickly calculate using calculator or your mobile? What? Where will the positive saturation occur at? Suppose you are giving 12 volt.
11.128. I mean
11.
28.
Okay, correct. Correct. 94 percentage of 12. So positive saturation will occur at 12 volt. Similarly, 5 volt, what will happen? These are the standard supply voltages that we will be. Okay, that is why I'm asking. 5 volt. If I'm giving 5 volt only.
4.7.
Okay, 4 point. Okay. Suppose V is 15 volt. Then where will negative saturation happen at? When V is minus 15. Okay. Minus 15, what will happen? How much will it be? Negative saturation. It will not go below that voltage. How much will that be? 15 voltage already we have calculated. So what will be the VSAT?
Minus of
Minus of
14.1.
14.1. Correct. So it will not go below minus 14.1. It cannot go below minus 14.1. So that is what is meant by saturation. Okay. So I will quickly show you in this NI multisim also something. I'll try because it is live. It may not work properly. I will show you the how it goes to. Okay. Okay. So in the left side, you can see this Opamp signal symbol. You can click on that. For the time being, I will take 3-terminal Opamp. So it is like this, correct? You have the Opamp. Now suppose I am giving some input voltage, okay, DC voltage. I am connecting to our non-inverting terminal. And I'm connecting the ground. Ground means 0 voltage, okay? So everything has to be what is that? And the negative terminal, inverting terminal, I am putting ground. Okay. Now suppose I want to measure the output voltage. Okay. So, oh sorry, give a junction here so that I can measure. Okay. So this is simply I have connected. So to the non-inverting terminal, I have connected 5 volt, and the inverting terminal I have grounded. So what is the differential voltage? What is the differential voltage between these 2 points? What is VID here? What will be VID? VID means what? V1 minus V2, correct? So 5 minus 0. So 5 volt is our differential voltage we are giving, because at positive terminal, non-inverting terminal, we have given 5 volt, and at inverting terminal, we have given 0. So 5 minus 0, 5 volt is our this thing. So what should be the output voltage? Output voltage will be, say for example, if it is a 2 into 10 power 5, correct, times 5, which is actually 10 power. Will you get 10 power 6? Will you get? Will you get this much high voltage? No, right? So how much will it be? It will be saturation voltage. It will be closely equal to whatever VCC supply you are giving. So if I click on this and go to setting, you can set what is the voltage that you are going to give. Okay. So this is the positive voltage. I'm going to give 12 and minus 12 we have given. So let us see how much output voltage we will get. Okay, I'm measuring the voltage here, output voltage. So now when I run this, you can see that it will be close to 12 volt. See here, I am not getting 2 in 10 power 6, correct? You are getting 12 volt, which is close to this. Actually, it should be 11.28. In practical, you can see that it will be 11.28. In simulation, it will show as VCC itself. Now see, suppose I am changing this voltage here. Okay. Earlier we have given VCC 12 and VE minus 12. Now let me stop this and give, say, suppose I am giving 5 volt. Then output also will be close to 5 volt. You can see that. Okay. VC, understood? It is 5 volt. It means that it cannot go above this bias supply we are giving. Okay. Suppose again I am changing this. I am changing this to say 20 volt. 20 volt positive supply and minus 20 volt negative supply. So you can see that it will be near to 20 volt. Output will be near to 20 volt. Are you getting the idea? Understood? Now I'll change this. Suppose, okay, I am changing this. Suppose I am connecting 5 volt here. Okay. And 0 volt here. Can you tell me what will be the output? Any idea? What will be the output? 5 volt I am giving to inverting terminal and 0 volt I am giving to, and this supply is 20. 20 and minus 20. What will be the output? Can you tell me? Anybody? Any guess? So what is VID here? Differential. Hmm? Differential input voltage, how much is it? Voltage at positive terminal minus voltage at negative terminal. What is the voltage at positive terminal? 0. 0 minus 5. Minus 5. So what will be the output voltage? Will it go to positive saturation or negative saturation?
Negative. So
Negative. So output will be minus 20. You can see that. See? Understood? It means that it cannot go below that voltage. Is it clear?
yes, sir.
Okay. But in this, I don't think it will work for micro. We will try and see, but I don't think it will work. Oh, it is working. Okay. Say for example, 5 micro volt I gave. Okay. So what will happen? I will open one sheet here. Okay. So input I am, okay, let me write like here. Okay, V1. Okay, V1 0 volt I gave. That is a non-inverting terminal ka voltage. Okay. And V2, which is the inverting terminal voltage, I gave 5 volt. Okay. So what is VID? VID is always voltage at the non-inverting terminal, that is V1, minus voltage at the inverting terminal. Correct. So it will become 0 minus 5, which is minus 5 volt. Micro, correct. Sorry. Microvolt I am giving, which means 5 into 10 power minus 6 volt. Okay. So this will become 5 times 10 raised to minus 6. This much voltage. And we are considering, for example, let us consider A as 2 times, which is the voltage gain of the op-amp, 2 power 10 power, 2 into 10 power 5. Then what is the output voltage? A into VID, correct? So A is 2 times 10 raised to 5 times minus 5 times 10 raised to minus 6. So how much is this? Minus 10 times 10 raised to minus 1, correct? How much is that? 10 into 10 power minus 1. How much is that? Minus 1 volt. Correct. So let us check whether you are getting 1 minus 1 volt. Ah, correct. You understood? You are getting minus 1 volt here. You got an idea?
Yes, sir.
Okay. But if I am increasing this, you can see that it will go to saturation. See, now it is in saturation. It will not go above that. Understood? Okay. Thank you all. Sorry, I took a little more time. Thank you all. You can leave.
Thank you, sir.